students, welcome to Eazy Btech, your guide for Btech and beyond. Here we are going to discuss signals and systems, and today's topic is continuous time elementary signals. It is a continuation topic or continuation session for the previous. Before going to our topic, this channel is very helpful to you for understanding Btech subjects very easily. So all of you share the channel, subscribe the channel. It is definitely benefited to you. Let's start our session, elementary signals. In this session, we are going to discuss sinusoidal function and exponential function. So two kinds of signals. Today's session we are going to cover sinusoidal and exponential. First we discuss about sinusoidal function. Sinusoidal function. Sinusoidal function or sinusoidal signal. Function or signal, same meaning. Okay, sinusoidal function. First I will write the definition, then we discuss what are the parameters in that definition. It is defined as continuous time sinusoidal signals defined as x of t is equal to a sine omega naught t plus phi. A sine omega naught t plus phi. Or we can also write cos. A cos omega naught t plus phi. Sine or cos functions, they are called sinusoidal functions. Sinusoidal means not only a sine function, we can also take cos function. So sine or cos, they are sinusoidal functions. So here letter A, what is A indicates? Peak amplitude. A is peak amplitude. Peak amplitude. And omega naught, frequency, angular frequency. Omega naught is angular frequency. Angular frequency. Units radian per second. Radian per second. And this omega naught we can also write 2 pi into f. F is the frequency in hertz. F is also frequency, but it is in hertz. So 2 pi into f, or f naught also we can write because I am writing omega naught. And f naught we can write 1 by t naught. T naught is time period. So this is about omega naught. And phi. Phi is the phase of or phase angle of sinusoidal function. Phase of sinusoidal function. Sinusoidal function. And one more important point, omega naught into t, this product. Omega naught into t, angular frequency into time, which is again phase angle or phase. If you differentiate phase with respect to t, what will be the result? Differentiation of omega naught t. What is the answer? Differentiation of omega naught t. Omega naught, what it is? Angular frequency. Angular frequency. So here the relation is What is the relation? Differentiation of phase. Differentiation of phase. d by dt of phase. What is the answer? Angular frequency. What is the answer? Frequency, angular frequency. Very important point. This point. Differentiation of phase is equal to angular frequency. Here, phi is called phase angle or phase of sinusoidal function. If phi is equal to 0, how is sinusoidal function? Here I am taking cases, 3 cases. Case 1. What is case 1? What is the case 1? If phi is equal to 0, phi is equal to 0, then the sinusoidal function x of t, a sine omega naught t, a sine omega naught t. And if you plot this waveform, if you plot it, how it is like a sine omega naught t. I am plotting it. A sine omega naught t. Here A is the peak amplitude. The positive peak is A and negative peak also A. Positive peak A, negative peak is also A. That means minus A. So first I am taking peak amplitude lines, dotted lines. So now it is a sine function. I am drawing now sine function. Neatly I will draw this one. Now the sine waveform we are plotting just like sine waveform, sine function. This is a sinusoidal function or sine function. Okay. So what is the amplitude here? Minus A. And what is the amplitude here? Positive side or positive peak plus A. So what is the phase of this? 0. Phase is 0. The waveform is this one. Here x-axis time. Case 2. If phase is positive, what is the case 2? Positive. Phase is positive. Case 2. If phase phi is equal to positive or it is positive, like pi by 2 or 90 degrees, pi by 4 or 45 degrees plus positive. If phase is positive, phase is positive, how is the waveform? The waveform is phase is equal to positive. Now first I will write the mathematical function of sinusoidal signal. X of t will become a sine omega naught t plus pi, positive phase, that is why plus pi. So the waveform is like now, the waveform is so peak amplitude is A only, means positive peak is A, negative peak is A. First I am taking peak amplitude line. So here, what is the peak amplitude? plus a, and here minus a. Now this is sine omega naught t plus phi. So the waveform is like this. Positive phase. This is the waveform we get. Okay, this is for positive phase. Now case 3, negative phase. Case 3 is phi is negative. The case 3, phi is negative. If phase is negative, how is the waveform? How is the sinusoidal waveform or sinusoidal function? Now I will write the function first. X of t will become a sine omega naught t minus phi, because phase is negative. Now the waveform, if you see the waveform, peak amplitude I am taking minus a plus a. Positive peak is plus a, negative peak is minus a. That is peak amplitude. Now the waveform is like this. So here phase is negative. Phase is negative. So these are the three cases with respect to phase phi. When phi is 0, it passes through origin. If phi is positive, above origin. If phi is negative, below origin. These are the three cases of sinusoidal function, right? For example, if you want to draw, here I am taking a value 3 sine omega naught t minus phi. So what is the peak amplitude here? Positive peak is plus 3, negative peak is minus 3. This is the clarity of 3 sine omega naught t minus phi. Positive peak is plus 3, negative peak is also 3, that is minus 3. Next, we discuss exponential function. We discuss about exponential function. These are also important. Exponential functions or function, exponential function. First we see types in this. We have two types: real exponential, complex exponential. Exponential functions, we have two types. The first one, real exponential. Real exponential. Real exponential. And the second one is complex exponential. Complex exponential. So these are the two types of exponential functions. We see one by one now. Real exponential, how it is defined. The first one, real exponential. We write the definition first. It is defined as x of t is equal to a into e power sigma t. This is the real exponential definition or mathematical expression or mathematical model. X of t equal to a into e power sigma t. Here I am going to take three cases of sigma. If sigma is 0, how is the signal? If sigma is positive, how is the signal? If sigma is negative, how is the signal? Three cases of sigma. The first case, sigma value I am taking 0. In the second case, sigma is positive. In the third case, sigma is negative. So three plots I am going to give: sigma 0, sigma positive, and sigma negative. Positive, sigma negative. The x-axis is time and y-axis is the signal which we are going to plot. X of t. Y is x of t. X is the time. Y is the x of t and x is the time. X is time. Now sigma is 0. Substitute here sigma is 0. What happens to x of t? What happens to x of t? A into e power 0 into t. E power 0. E power 0 is 1. So it will be a. A means what? Constant or a DC. The amplitude is a. So draw a constant line having amplitude a. That is the answer now. So I am plotting a now. This is the a. Its amplitude is how much? What is the amplitude? A. So this is the answer. If sigma is equal to 0, we are getting constant. If sigma is positive, like 1 or 1.52, sigma is positive, then how is the waveform? We get exponentially increasing. The result is like this. Exponentially increasing. Sigma is positive now. The signal increases exponentially. I will draw neatly. I am erasing it. Signal is increasing exponentially. That's all. This is the result we get. Sigma is positive. This point is A. Because at t is equal to 0, we get A. Here sigma is greater than 0 or positive. Exponentially increases. That point I am writing. Exponentially increasing. Exponentially increasing. If sigma is negative, opposite to second case, sigma positive exponentially increases. If sigma is negative, it exponentially decreases. Simple. Like -1, -2. You take sigma values, then we get exponentially decaying or decreasing. So that is the result. Exponentially decaying or decreasing. So this is about real exponential function. X of t equal to e power a into c power sigma t. Sigma value 0, sigma value positive, sigma value negative. The next one, exponential, complex exponential, complex exponential. Complex exponential. The definition first we write. It is defined as x of t equal to like e power st. E power st. Exponential means e power only. So here e power st. What is s? S is complex variable. What is s? Complex variable. What is complex variable? Like sigma plus j omega or omega naught. Complex variable, it contains real part and imaginary part like a plus jb. So sigma plus j omega naught. Here sigma is real part and omega naught is imaginary part. Now if you go and substitute in this e power st, what is s? Then we get e power sigma plus j omega naught into t. That's all. Just I am substituting s. S is a complex variable. This can be written as e power sigma t into e power j omega naught t. Right or not? Here in the power we have plus. I am writing bases into. In base into. So what is this part? Already we discussed previously. E power sigma t, real exponential. Right? Here we can take three cases. Sigma is equal to 0. Sigma is positive. And sigma is negative. Sigma is negative. I am going the same cases here also. Sigma is 0. What happened to x of t? X of t will become e power j omega naught t. E power j omega naught t. It is like e power j theta as per Euler's formula. Cos theta plus j sin theta, that is cos omega naught t plus j sin omega naught t. Cos omega naught t, j sin omega naught t. This is called, this expression or this function is called sinusoidal. What we call sinusoidal function. Already we discussed sinusoidal function. So the waveform will be like, sinusoidal means you know the waveform is how. So I am plotting either sine or cos. So this is the sinusoidal. So this is the case 1. This is case 1. If sigma value is equal to 0, we get sinusoidal function having constant amplitude, fixed or constant amplitude. Amplitude levels are constant. Constant amplitude. This is the case 1. Now case 2. What is case 2? Sigma is positive. If sigma is greater than 0 or positive, then how is x of t? X of t is e power sigma t into e power j omega naught t. Right or not? So what is here e power sigma t? Already we discussed. It is a real exponential. Sigma is positive, so exponentially increasing you get. Exponentially increasing. It is exponentially increasing. Now already we discussed only about e power j omega naught t. It is a sinusoidal. It is sinusoidal. What is the result? Here we have multiplication. So what is the result we get? What is the result we get? Exponentially increasing sinusoidal. That's all. Exponentially, this is the result. Increasing sinusoidal. Increasing sinusoidal. If you see the waveform, the plot, we can understand better. Well, we can understand. This is y x-axis, y and x. Now exponentially increasing sinusoidal, like in this manner. Exponentially increasing sinusoidal. Increasing sinusoidal. So oscillations are increasing, right or not? Why oscillations are increasing? Why oscillations? These sinusoidal oscillations are increasing. Increasing. Why? Because of this e power sigma t. Here sigma is positive. That is the reason. Understand? Next, go to sigma is less than 0. Opposite to greater than 0. Case 3. If sigma is less than 0 or negative, we can call, then x of t will become e power sigma t into e power j omega naught t. Is it right? So already if sigma is less than 0, what it gives e power sigma t will become? It will become exponentially decreasing because sigma is negative. Exponentially decreasing. Right or not? After that, we have this term e power j omega naught t. It is a sinusoidal. It is a sinusoidal. What is the result of this now? Again, multiplication, we have exponentially decaying multiplied by sinusoidal. The result is exponentially decaying sinusoidal. What is the result we get here? Exponentially decaying sinusoidal. I am writing result exponentially decreasing or decaying sinusoidal. Decreasing sinusoidal. The same thing I am going to plot. Whatever the result we have, I am showing with waveform or plot. Right? So decaying sinusoidal is exponentially decaying. Decaying sinusoidal. Okay. This is the answer now. So these are the three cases in complex exponential signal. Right? So by this we have completed continuous time elementary signals. Very, very important. Why we need to discuss about continuous time signals or elementary signals? Why we need to study? Because these are input signals. These are input signals. We can use them as input signals to study the behavior of the system. To know the behavior of the system, we need input signals. These are input signals. Very, very important. Okay. Thank you, students. Thank you for this class. We meet again. Please subscribe, share, and inform to your friends so that they also get knowledge easily. Thank you. Thank you all.